Chapter 17, Sound Waves. In the previous chapter, we studied some general properties of waves. Now we're going to focus our attention on a special type of wave, the so-called sound wave. The study of the sound wave is known as acoustics. So this chapter will be a brief introduction to acoustics. So what is the physical nature of sound? When you hear something, what is going on? Well, let's say we have a tuning fork, right? And when you strike it with a hammer, it's going to start to shake, right? It's going to start to shake like this. And the shaking of the tuning fork causes the air around it to move around. So the air molecules, they move randomly, but that does nothing to produce any collective motion. And so even though the air molecules move randomly, if there's no source of disturbance, such as the tuning fork, you don't hear anything, right? But if there's a source of disturbance, then the air molecules will start to move collectively, okay? And as they move, some parts of the air will get compressed, some parts of the air get decompressed, and so there is going to be variation in density. And as we know, the denser the medium is, the greater the pressure, if everything else being the same. So you're going to create a pressure variation from place to place as well. And the pressure variation will cause an imbalance of force, and that starts to move even more air molecules. So you can see, starting from the source of disturbance, which is the tuning fork, you're going to have this ripple effect where the movement of the air around this tuning fork causes a pressure imbalance, which pushes more air molecules to move around. And this motion eventually will be felt over here. And this is where your eardrum is. Your eardrum is a membrane which will vibrate if being pushed by the air around it. And this vibration will be registered by our brain, and then we will hear the sound of this tuning fork. Okay, so clearly you have a disturbance that started from this tuning fork, which is the source, and went through the air, which is the medium. So therefore, by definition, this is a wave. So as you know, wave is basically, the oscillation that propagates through a medium. Right? So that certainly qualifies as a wave. And the special type of wave we're talking about here that has to do with sound, you can think of it as a displacement wave. Displacement wave because the air molecules do move around, but this displacement of the air molecules also cause a pressure variation. So you can also think of it as a pressure wave. Okay, so this is a brief statement of the physical nature of sound. But if you want to get a better understanding of that topic, a good idea would be to study the equation that governs the sound wave. The derivation process will allow us to better understand the physical nature of sound. Now, as we know, and when you compress something such as air or water or any three-dimensional substance, the pressure will increase. Okay, the response of the system under pressure can be characterized by the so-called bulk modulus, which we studied in chapter 12. So let's first review the concept of bulk modulus because we'll be using it in our derivation of the sound equation. So here is a three-dimensional piece of substance. Okay, its original volume is V naught, and that is indicated by the outer profile in this drawing. Now suppose I apply a pressure in all directions. Under this pressure, the thing gets smaller, okay? The volume decreases by an amount delta V. So how much delta V do we get out of this pressure? Well, this is described by the bulk modulus, as you learned from the previous chapter. So I'm going to rewrite and write down the bulk modulus definition again. Delta V, what is delta V equal to? Well, delta V is proportional to V naught, as we know. Okay. And it is also proportional to the amount of pressure that we get. I mean, the original pressure is P, capital P, and that's just there. Under the capital P, there is no extra deformation. But on top of that, if I put a small p, okay, so you notice, be careful here, there are two different letters, a capital P and small p, they look very similar. This is the original pressure. And then you have a small pressure, which I should really use a different letter here, delta P. Okay, delta P. So delta V is proportional to delta P. Clearly, it's proportional to delta P. Okay, but it also depends, delta V also depends on how strong the material is, how resilient it is to deformation. So I use a so-called bulk modulus to describe that. The greater the bulk modulus, the stronger the material, therefore the less delta V. So therefore I'm going to put a 1 over B here, not B, but 1 over B, such that the greater the bulk modulus B, the smaller delta V. And that's how we define delta V, that's how we define the bulk modulus B, except don't forget there is a negative sign in front of it, because as we increase pressure, so when delta P is positive, you will yield a negative change in volume. So delta V would be negative for a positive delta P. That's why I have to use a negative sign in front of the right-hand side to balance it. Okay, so we can write, I can solve for B and write B equals negative delta P, and then divided by the fractional change in volume delta V over V naught. Okay, so that's just a review of the definition of bulk modulus we learned in chapter 12. And as we derive the equation of motion for sound wave, we'll be using this concept, because after all, as the air molecules move due to the sound wave that's present, it's going to cause a variation in pressure, and that pressure causes a compression of the air. So we'll see that. So now we're ready to write down the equation of motion for air and solve it, hopefully. So for simplicity, let's consider a column of air so that the cross-sectional area does not change. It's A. So imagine we have a column of cross-sectional area A, okay? And so there's air trapped inside. Now, let's consider a small segment of the air in that column. Why such a small segment? Because the pressure and displacement vary from place to place. Right? It's not uniform. So we have to isolate a small piece when you have a non-uniform situation. So imagine we have a small segment of the air, which without any sound wave would start from here and end up there. Okay, so it's between x and x plus dx. I'm using a coordinate x to indicate the position of air inside this column. So initially, I'm looking at this column without any sound wave. It will start from here. It will end up there. Okay, that's initial. Now, what happens if there's a sound wave present? Well, first of all, the air pressure no longer is a constant. Okay, before you introduce any sound wave, the air pressure is just P naught everywhere, just P naught. Okay, but on top of that, due to the sound wave, now you have an extra factor in the pressure. So the pressure introduces, there's a new term in pressure, that's delta P. So the total pressure at a given location is P naught plus delta P. Okay, that's the total pressure right here. P total. This is P total. Okay, total pressure right here. But P naught is uniform and constant. It doesn't change. Okay, it's just whatever pressure is already present without any sound. But delta P, on the other hand, is variable. It varies from location to location and from time to time. Okay, so this is the delta P that assumes the shape, assumes the form of a wave. So you can think of, if you plot pressure as a function of time and location, you can think of the plot like this. So originally you have P naught. Okay, so let's say this is how it depends on x at a given moment, or you can also, you also can plot as a function of time as well. Let's say initially it's P naught. So initially it's just a straight line like this. It doesn't change as x changes. But now on top of that, I have a variation. Okay, I have a variation like this. This variation is delta p. This variation changes from place to place and from time to time. Okay, so that's what it is. All right. Now, when you have the reason why you have delta p is because the density of air is no longer uniform over time and over space. In some locations, you have greater amount of concentration of air molecules, therefore the pressure over there is higher, so delta P will be positive. And in some other locations, there will be less air molecules present per unit volume, therefore the pressure decreases, so at those locations, delta P will be negative, and so on. And of course, that is all because of the movement, displacement of the air molecules. So so whatever accompanies delta P has to be the displacement of the air molecules. Okay, so we have two waves that together produce the sound, and they are related to each other. One is the pressure wave, delta P, not P, but delta P. Okay, I mean the P is the total wave, and of that P, the dominant part is actually P naught, but that P naught is fixed. It doesn't change. A very tiny fraction of total pressure is delta P. That's the part due to the sound, but that's the part we're interested. Okay, again, delta P is caused by the movement of air molecules. So we have another wave which accompanies that, and that is the displacement wave. Clearly, they together produce the sound, and they're related. Okay, they're definitely related, these two waves. Now, so here's what happens when you add a sound disturbance to this column of air. Initially, again, it's from here to there, but now both edges, the left and right edges, they both move. Okay, they both move, and the left edge moves by an amount x. I'm sorry, s. So let me write that. Let me draw that. Here is the movement of the left edge of this column of air due to the sound wave that's present. Okay, let me make sure I use a different color to differentiate that from X. S and X are totally different things, so please pay attention to that. Okay. So here is S. So the left edge of this column went from here to there because of the disturbance caused by the sound wave. Now, if the right edge also moves by the same amount from here to there, also by an amount S, then the entire column has just shifted, but the volume did not change, did it? Okay, I'm assuming the cross-section area does not change. Okay, and the length remains, the length of this column remains dx, right? So therefore, it's not getting compressed, nor does it get decompressed, and therefore the pressure remains the same as P naught. And of course, if there's no variation of pressure, then it doesn't cause the this column of air does not lose any mechanical balance. It will not accelerate, and it's not going to vibrate. There's no sound wave. But the thing is, the left edge and the right edge will not necessarily move by the same amount. Okay, so the left edge moves by an amount S, and the right side moves by an amount S plus ds. Okay, here is ds right here. So it moves a little bit more or a little bit less than the left edge. That's what causes the column to increase or decrease in its volume. So suppose ds is positive, then there's an overall increase in the volume of this column, right? Otherwise, if ds is negative, it's getting compressed. Okay, so there is a change in the volume of this column, and that results in a change in the pressure. Right. So let's see what kind of equation we can write for S and for delta P. Okay, the idea is we're going to apply Newton's second law to this column. Okay, to this column, F equals ma. F is the net force in X direction caused by the pressure imbalance on the left and right edge. Okay, and so let's start this process. Let's write down F equals ma for this column. And let's see, what is F, what is M, and what is A. So you write F equals an A. And F is, again, caused by pressure variation. Okay, so you see on the left-hand side, I have this, I have this much pressure on the left-hand side, pushing on it. And on the right side, I have that much pressure pushing on it. And clearly, they're not equal to each other. Why are they not equal? Because delta P is not the same on the left and on the right side. They both have P naught, so that cancels out. But the left side has a delta P that's different from delta P on the right-hand side, because delta P is a function of X and T. T is the same. We're looking at what happens at one moment, but location is not the same. Okay, so the left edge and right edge, they don't have the same value of delta P, and as a result, there will be a net force. Okay, so let's see what is the net force equal to. Okay, so on the so the force pointing to the left, I'm sorry, pointing to the right. I'm using the right as positive. Okay, so the force pointing to the right is pressure on the left side times the area. Okay, so pressure on the left side, as you know, it's this much. That's pressure on the left side, right? So you get this green arrow, which is the force pushing this column to the right, which we consider positive. Okay, positive x directions, that's positive x direction. So the force pointing to the left is P naught plus delta P at X and T. Okay, multiplied by the area A. You know, pressure times area, isn't that equal to the force? Okay, so that's a positive force because it pushes to the right, to the right. Now, there's also a force pushing backwards, and that's the force coming from this pressure, right? So you get this green arrow pushing it to along the negative x direction, and how much is that force? Well, that force, first of all, it's negative. I'm adding a negative sign here, and the magnitude is again pressure times area. Pressure here is P naught plus delta P at a new location of x plus dx. And of course, the time is the same, looking at what happens at this one moment. Okay, times the same area. And that is F. Okay, that is F. Actually, that F is very small, so might as well just call it dF. So I'm going to call it dF. And that reason why it's only dF is because the mass is only dm. dm is the tiny mass of this tiny slice. So we have dF already. And then let's look at mass. Okay, dm. What's dm equal to? Well, dm is just the mass content in this region. Now remember, the volume can change. Because the thing can be compressed or decompressed, but the mass does not change. Okay, unless you got particles going in and out, which is not the case. You take the same amount of particle of air molecule, you just compress or decompress it. So you change the volume, but not the mass. So the mass is just density times volume. Density is rho, and that's the rho. That's the uniform rho before any sound wave is present. We have to multiply this by the original volume. Okay, so the original density times the original volume, that equals the original mass, which does not change even when the sound wave is present. What is the original volume? Original volume is area A times the original length of this column, which is dx. Okay, so dm is rho dv, which is just rho A dx. That's simple. Okay, so you have df, you have dm, and what about A? Well, A is a second derivative of some sort of displacement, isn't it? Okay, I have two quantities with the same dimension as displacement. One is s, the other is x. Which one do I use? Well, be very careful here. This is a point of confusion in a lot of people. Does x change over time? What's x? X is the original position of the left edge of this column. X plus dx is the original position of the right edge of this location, of this column. They do not change, okay? They do not change. But what changes is S. S is the movement of this side, of the left edge of the column. And S plus ds is the movement on the right edge of this column. both edges, the left and right edge, can move back and forth. So S can be positive, negative, positive, negative. S is the true quantity that can change over time. So when we talk about the movement of this column, it's not X. X simply tells you where the edge initially was. Okay, that does not change over time by definition. S is the displacement of the left edge, and that is the quantity that changes. Now, so therefore, the acceleration should be the second derivative of S with respect to time. So A equals to what? The second derivative. You notice I did not use a regular derivative d squared x, d squared s over dt squared. It's because s is a function of both location x and time t. I'm only taking derivative with respect to t, and therefore I cannot use the normal derivative sign. I have to use the partial derivative sign. Okay. So I have df, I have dm, I have a. So I have all these three. So let's plug in all these three into Newton's second law above. And what do I get? I get this. I get, first of all, let me clean the right-hand side of the expression for df. I know that a lot of things cancel out. P naught cancels here. And then the difference here is you have delta P at this location, you have delta P at that location. And so let me rewrite df. Let me clean df somewhat more, okay? So before I write down Newton's second law, let me clean this df a little bit more. So let me write df is equal to, okay, negative delta P at x plus dx and t minus delta P at x and t, and then times a. Okay, I just took out a negative sign. But, you know, this thing that you see here is the value of a function at x minus dx minus the value of the same function at x for the same moment. If I divide this by dx and then multiply this by dx, what do you think this is? What do you think this is in the bracket, this whole thing here? Isn't this the derivative of delta P with respect to x while keeping t the same, right? So by definition, well, what I have here is negative partial delta P over partial x, isn't it? By definition, right? And don't forget, there is an a and there's a dx. Okay, so that's how I clean up df. So with that, I can plug in all of these into df equals dm times a, and let's see what I get. And therefore, f equals ma reduces to the following: negative partial delta p partial x a dx, that is df, okay, equals dm times a. Dm is, again, rho a dx, that's dm. Okay, times a, which is the second derivative of s with respect to time. So this is what Newton's second law tells us. Okay, I can cross out the a's on both sides and cross that out and cross out dx on both sides. Then I have this. Let me use a different color now. Let me use, let's say we use a green color, okay? So I have partial delta P, partial x equals what? Negative rho partial s squared over partial t, second derivative s with respect to time. So here's my first equation that I'm gonna keep in my derivation of the wave equation. It's not the ultimate equation that I'm looking for. Reason being, there are two unknown functions here. They're mixed together. One is delta P. Okay, one is delta P. The other is S. They're both functions of time and space. See that? See from here, they're both functions of time and space. So I cannot only have this one equation because I have two unknown functions. So it's not going to it's not going to be able to produce a unique solution for me. I need another equation. Okay, two unknown functions, therefore two equations. All right. So what's that other function? Well, look, I said delta P and S, they're related. The reason why there's a delta P in the first place is because there are movements of the left and right edges of this thing, of this column. And if they move by the same amount, if S on the left and S on the right are the same, then delta V is 0, therefore delta P is also 0. Okay, delta P is the actual pressure caused by, you know, the variation in the volume of a given amount of air. So therefore, the reason why there is a delta P is not only because there is movement S on both sides of this column, but also because S is different for the left hand side and right side. And therefore, it's not S that matters, it's DS that matters. Okay, if there's a DS here, if there's this DS here, that's what causes the two edges to move by a different amount. Therefore, that's going to cause the volume of this piece highlighted in yellow to change, and that will correspond to a response to the system. So this change in volume produces an extra pressure, and that is given. The relationship is given in the bulk modulus. Okay, the bulk modulus equation. So therefore, at this point, I'm going to apply the bulk modulus equation to relate delta P and S. Okay, so I'm going to apply the bulk modulus definition to this column of air, this column highlighted in yellow. Okay, the bulk modulus equation, once again, I'm going to first write down the bulk modulus equation, the generic equation. It says that B equals to negative delta P over delta V divided by V naught. Delta V divided by V naught. That is the generic definition of the bulk modulus. But in our case, what is delta P? What is delta V? And what is V naught? Well, let's see here. This bulk modulus for the air, okay? Negative, what's delta P? Delta P is the additional pressure caused by the sound wave. And in our case, delta P actually changes a little bit between the left-hand side value and right side value, but the change is pretty small. Okay, delta P itself is already pretty small. The change in delta P between left and right side is even smaller. So it's just that delta P. In the generic expression, delta P is just the same as our delta P, okay? It's the same as our, do not confuse that with P naught. P naught is the ambient pressure, and that never changes. Okay, you divide by delta V over V naught. What's delta V? Delta V is the change in volume. Okay, what's the change in volume? Well, the change in volume is because the left edge and the right edge move by different amount. In our case, the right edge moved by an extra distance of ds. Therefore, it claims an extra volume, which is A times ds. Right? So the overall change in the volume is A times ds. A times ds. But what is the original volume V naught? We're talking about original V naught of this yellow region. Okay, this region highlighted in yellow. And originally the cross-section area is A, and the thickness is dx. So original volume is A dx. So let me rewrite this. This is just negative delta P times what? Cross out the A. 1 over ds over dx. In fact, I flip that over, that's dx. That becomes dx over ds. Okay. Or let me rewrite it like that. I'm going to keep this delta P in the numerator as is, but I'm going to change the notation on the denominator a little bit. A is gone by crossing out. Instead of ds over dx, I should do partial s over partial x. Why? Because because S is a function of not only X, but also T. And when we look at this diagram here, T is the same for every point. Okay, I'm just taking a snapshot of this whole thing at one moment. The T doesn't change. So when you take derivative, T is kept as constant. Therefore, you have to use partial derivative. This is a desired second equation. Okay, in fact, I can solve for delta P from that equation. Then I get, again, I'm going to use green now. So delta P equals what? Equals negative B partial S partial X. Okay, so that's the second equation. Remember, I need two equations, one because I've got two unknown functions, delta P and S. I got my two equations now. Okay, so let me box that. So all I have to do now is to get rid of one variable and solve and find the equation for the other. So then I have my wave equation. You can find a wave equation either for delta P or for S. Okay, let's say, for example, I want to eliminate delta P. I just want an equation for S. Let's see what I get. Okay, now, so I have equation number 1. And I get equation number 2. How do you eliminate delta P? It's very simple. Just plug in delta P in the second equation into the first equation. It's just that simple. Okay, so let me see what I get. So then I get partial X of delta P, but delta P itself is negative B partial S partial X from the second equation. So negative B partial S partial X. That will give you negative rho times this second derivative respect to time. Okay, this differential equation has no delta P anymore. There's only S as the only unknown function. So let's clean that up a little bit. Let's get rid of the two negative signs on either side. And let's complete the second derivative on the left-hand side. Then I have the second derivative of S respect to X, partial derivative, okay? Equals what? Rho over B, because I have to move that B to the other side now, times the second derivative of S with respect to time. Okay, now this is a partial differential equation of the second degree or second order, because it gets into the second order derivative. Okay, let me box it first. Doesn't do a good job, but I'll try one more time. Okay, so here is my equation. I found the equation for S. You can also eliminate S instead, get the equation for delta P. You'll find the exact same result. Okay, both delta P and S satisfy the exact same equation. Doesn't mean the solution is the same, but at least the equation is the same. And this is the equation for the sound wave. Okay, equation for the sound wave. Otherwise known as the wave equation. Why do we call it a wave equation? Well, you already saw from chapter 16, we saw a generic wave equation for the wave on the string, right? And let me write that down for comparative purposes. Back then, I found this. I found that's from chapter 16, right? Look at the similarity. Okay, I mean, we replaced y with a new variable s. Okay, y is in the perpendicular direction, to s for the wave on the string. But here we have a movement s along the same direction as x. But otherwise, they're really the same thing. The solution should be the same. If you can solve this generic equation in chapter 16, that's the wave equation. That's the generic wave equation. You should also be able to solve this equation in red, which is the equation for the sound wave. Okay, And we learned something very important by comparing these two equations. I found that 1 over v squared equals to what? Rho over v. So that tells me the speed of the sound wave. So v equals the square root of b over rho. This is the equation for the speed of the sound wave. Okay, very important. So not only did we find the equation in the derivation process, we had a better understanding of what sound wave really is. The physical nature of the sound wave is really caused by the movement of the air column. See that? The air column move by different amount at different locations. That causes the air to either compress or decompress, which causes a pressure imbalance. Okay, and that pressure imbalance results in a net force, which drives the air column to move. So it causes a displacement wave. So we can either think of it as a pressure wave or displacement wave, and they're clearly related in the second equation right here, equation number 2 right here. Okay, so you can either solve for S or solve for delta P. You will get the equation for the wave, for the sound wave. All right, and we also found the speed of the sound wave. And in fact, it is consistent with a general idea, and that is for an elastic wave, the speed of an elastic wave is always the square root of some sort of elastic modulus divided by some sort of density inertia parameter. Here, the elastic modulus is the bulk modulus, because clearly we're talking about three-dimensional medium, so it's not Young's modulus, which is for linear displacement, linear distortion. This is three-dimensional, it's bulk modulus. And the inertia, we're not talking about the total mass of the entire air column. Doesn't make any sense, because clearly, the bigger the column, the greater the amount of mass. Doesn't mean air travels any faster or slower in a bigger column, right? It's the density, it's the mass per unit volume that really matters, so that it makes sense to see the expression of square root of b over rho as the speed of sound. All right, so that is our first lecture. And in the next lecture, we're going to take a closer look at the speed of sound expression and see some typical values for the speed of sound. We're also going to look at the general solution to this wave, to this wave equation, and apply it to a special case when there is a single frequency, otherwise known as a sinusoidal wave. So that's all coming up in the next lecture.